Tonight's episode of AP Chemistry is brought to you by lightly sweetened all-natural Snapple, made from the best stuff on Earth. TM. All right, we're going to talk about how to calculate the pH for a weak acid solution. So in the case of hydrofluoric acid that we see here, it's a weak acid, not because it doesn't hurt you, doesn't burn you. In fact, hydrofluoric acid is one of the most dangerous acids in the world. This is the one acid that a single drop would actually kill you. So strength has nothing to do with whether or not it's deadly. What it does mean, though, is that when this solution, when HF is put in liquid, it sets up an equilibrium because left inside of the solution, there's going to be HF, H+, and F-. There's actually going to be 3 players in here. So in order to figure out the pH, remember the pH, it deals with the concentration of H+. And since this is a weak acid, we're going to need to go through a calculation to figure out what the concentration of that H+ is. All right, and so to do this, since it is an equilibrium problem, we can set up an equilibrium equation to figure it out. And the best way, of course, to do this is with an ICE table. So let's go ahead and set this up in an ICE table. So ICE. It's been a while since we've really had to use these. So remember that I stands for initial, C stands for change, E stands for equilibrium. So initially, we need to go through and figure out how much of each of the components is in this solution. So notice how all 3 of them are aqueous, which means that all 3 of them are going to be in the solution. So initially, we have 2.5 molar HF. Let me go ahead and change my colors so we can see this a little better. There we go. So 2.5 molar HF, and we're going to say that in the instant before it actually dissociates into H+ and F-, we're starting off with 0 H+ and 0 F-. Now it changes. So in order to reach equilibrium, in order for it to dissociate and create that concentration ratio, it needs to go through a change. And so we're going to say that in order for H+ and F to go up, HF is going to need to decrease. And so we're going to say it's going to decrease by some unknown variable as of yet. We'll call that x. So it will decrease by x. And if it decreases by x, then H+ and F- are going to have to increase by x. Now all 3 of those numbers will be the same. They'll be the same magnitude, just it's going to decrease in the case of HF, and it's going to increase by that amount in the case of H+ and F-. And since it's all a 1-to-1-to-1 ratio, they're all going to be the same magnitude. Now, at equilibrium then, so once it reaches that perfect ratio where everybody's happy, it's going to equal a certain amount, and it's going to equal 2.5 minus x. So since HF starts at 2.5, decreases by x, that means at equilibrium it's going to be 2.5 minus that x amount. H+ starts at 0, increases by x, so at equilibrium it's going to be at positive x. F- starts at 0, it increases by x, so at equilibrium it will also be x. Now that we have that information, we can take those values and we can plug them in up top into the Ka equation. So we do know what Ka equals. Ka is 7.2 times 10 to the negative 4th. So let's take these variables and numbers and plug them into an equation. So I'm going to go to a fresh screen, but remember these values that you see on here. Alright, so we know that the Ka for the solution, well, we know the value of that. And then we can write out the Ka expression using those 3 things that are found in the solution. So remember, all of those are aqueous. That means all of them are going to be in there. It's going to be the concentration of the reactants or products. So the concentration of H+ times the concentration of F- divided by the concentration of HF. So all 3 of those will be left in the solution. If this was a strong acid, then this guy right here would be in the solution in a very, very small amount to where we would consider that to be nothing and just the ions. But since this is a weak acid, it's going to be mostly the HF with some H+ and F- as well. And we know the value of Ka to be 7.2 times 10 to the negative 4th. Alright, so on our little ICE table before, we got the values of those different concentrations, these guys up here. We said that H+ is going to be x, F- is also going to be x, and that HF is going to be 2.5 minus x. write that in then. So we'll say that Ka is equal to x times x divided by 2.5 minus x. Now, if you remember back to the original equilibrium section, oops, sorry guys. We had that rule of approximation, and let's take a look at that again because that's going to become real important here. So this 2.5 minus x. Let's figure out if that minus x really matters. It's the whole thing. If you have $1 billion and you give someone a nickel, you still got $1 billion. So if x is small enough, it doesn't matter if you subtract it from 2.5. It's not really going to affect that number. And the way you test that is by taking the value that you have for Ka and plugging it in for x. So if we take then 2.5 and subtract from it the 7.2 times 10 to the negative fourth, and if you plugged it into your calculator, it still equals approximately 2.5. So really, this minus x doesn't matter, and we can take it out of there. It's going to make the equation a lot easier to solve. If you didn't take that minus x out, you would still get the same answer, but you'd have to use the quadratic formula to get there. And never in the history of the AP test have they required students to use the quadratic formula. So more often than not, you can cancel out that minus x. So let's solve this equation then. We know that this all equals 7.2 times 10 to the negative fourth. So we can take this equation and we can rearrange it to see that x would equal the square root of 7.2 times 10 to the negative fourth, and that would be multiplied by, also in the square root, 2.5. So feel free to pause real quick and solve for that x, but when I solve for x, I find out that its value is 0.042. So here's what that means then. If we go back to our main screen, we look at our ICE table, we can see here that the concentration of H plus is going to be equal to X at equilibrium, and the concentration of F minus is going to be equal to X at equilibrium. So all of those, we'd say that the concentration of F is equal to the concentration of F minus, the concentration of H plus is equal to the concentration of F minus, which is equal to our X value, which was 0.042 molar. Now what we're concerned with here is not necessarily the concentration of the F minus. That's not going to affect the pH at all. We're looking at the concentration of H plus. So we found now that the concentration of H plus in this solution at equilibrium is the 0.042. So if we clear this out, and we can now do the pH calculation with this finally. And so what I hope you notice here is that the concentration of H plus, 0.042 molar, is much smaller than the concentration of the solution itself. If this was a strong acid, the concentration of H plus would be 2.5. Since this is weak, the concentration of H plus for this particular acid is only 0.042. So it's a very, very small amount of dissociation. And if we take the negative log of the concentration of H plus, 0.042, we can get our pH, and the pH then would be 1.38. Alright, so at this point, this is the end of this particular lesson. If you want some extra practice, if you want to try this one out, here is another problem for you. So find the pH of a 1.5 molar HCN solution. So I'll solve this one, but at this point I'd say pause the video, give this problem a shot, and then if you need some help you can turn it on and take a look, or just scroll ahead to look at the answer. If you feel really confident, just want to go to the practice problems, you can skip the rest of this video. Welcome back. So here is how I solve this problem. So of course I set up an ICE table right away. Since this is a weak acid, we know it's not going to go all the way to completion. And we have 1.5 molar of the HCN, and both of those are going to start out at 0. HCN will decrease by X, H plus and CN will both increase by X, and then at equilibrium, the hydrogen cyanate is going to be at 1.5 minus X, The hydrogen, the protons are going to be at plus x, and the cyanide is going to be at plus x. So we could take our Ka value and we can use our equilibrium concentrations, plug them all in to solve for our concentration of H+. So I'm going to go to a blank screen to do that. So we know that Ka in this case was 4.9 times 10 to the negative 10th. And it's the concentration of H+ over times the concentration of Cn- all over the concentration of the undissociated HCN. So we've got our equilibrium values that we just looked at back in the last slide. Now we could take those and plug those in for these values. Ta-da! There they are. So like always, or like typically, we can assume that this minus x is not going to make a difference to that 1.5, so we can get rid of it. And if you take a look, 4.9 times 10 to the negative 10th, imagine 9 zeros in front of that 49, it's not going to change 1.5. So then we solve out this equation, we can get the x values, and we would find out that x equals 2.7 times 10 to the negative 5th. And if we take that back to the slide before this, we can remember that HCN at equilibrium was 1.5 minus x. This was plus x and plus x at equilibrium. And since we're concerned with H+, its x value would have been the concentration, which was 2.7 times 10 to the negative 5th. So our H+ concentration, 2.7 times 10 to the negative 5th. And if we negative log that, we get our pH, and our pH is 4.57. All right, you have some practice problems to do with those too, so if you need a little extra help, that's the place to go. And then write down any questions you got about these, because this is going to be a big part of this unit is solving for Ka. Get a little bit trickier than this, but this is a good starting point.